So just to sum up here, thinking about efficiency of searching, we've talked about how linear search is O of n, it's linear. Binary search is O of log of n, it's logarithmic. So obviously binary search is more efficient, it's faster than linear, but it does require sorted data. Now, even our most efficient, fastest sorting algorithms are n log n. So that is less efficient than just O of n, right? So you really have to know your data, you have to know what you're doing to think about, does it make sense to sort my data and then use binary search, which is going to overall make my algorithm n log n? Or does it make sense to just leave my data unsorted, if it is unsorted, and just use linear search, making my overall algorithm O of n? Now, certainly if you already have sorted data, binary search is the way to go, most likely, right? Because it's more efficient. But if you have unsorted data, you really have to think about it. And some of the things to think about are, how often are you doing the search versus how often are you doing the sort? Now we're getting into, again, sort of real world considerations, because if you do a sort, n log n, followed by a bunch of binary searches, your whole algorithm is still going to be n log n, right? So that is still a higher order of growth. It's less efficient than if you were just to leave it unsorted and do an O of n linear search. So from an order of growth big O perspective, that's always going to be less efficient. But you have to look at the real data, right? So you have to look at the actual time. Again, if I am in real timing terms, if I am sorting once and doing a million searches, I probably would opt to do a sort followed by a million binary searches, right? If I am searching, if I have to sort every time I need to search, right? So let's say I sort my data, then I'm adding in some new data before I search. So I have to go sort, search, add new data, sort, search, add new data, sort, search. In that case, that's probably not worth it to do your sort. And you're doing that a million times. That's probably not worth it to do sorting. You probably want to do linear search, or maybe use some different kind of data structure altogether as opposed to just a flat array or a flat list. But anyhow, these are things you have to think about. The big O efficiency matters, but your real world timing matters too. And in order to figure that out, you really have to know your data and you really have to know what you're doing with it in order to decide what's best. So when thinking about that, one other thing to think about is, are you using data that uses linked nodes? If so, you don't really have a choice. You got to use linear sequential search. Okay, you can't really do binary search on linked implementation. So if you got linked implementations, it's not really a hard choice. But if you have an array or an array-based list or something like that, yes, then you got to think about, is it sorted? Well, if it's not sorted, you basically have to use linear search. Or again, you can consider sorting, and this depends on how often do you want to do the search, how often are you going to be doing the sort, right? If you're only doing a couple searches, probably not worth the sort, right? So if you have a million elements, but you only need to do 2 searches, probably wouldn't sort it first, right? So the efficiency probably isn't worth it. The saving of time, I should say, probably isn't worth it. So you got to think about that. If you have an array of sorted data, again, remember that this means that your items have to most likely somehow implement comparable. It assumes that because you can't do binary search otherwise, then you probably would use binary search. You could use linear search. It's definitely possible, but most likely you'd choose binary. Now, let's say you have a million size sorted data set, but you know that 95% of your search entries are going to be in the first 1,000 positions. Well, then maybe use linear search, right? Again, it relates back to this idea that you need to, in a real world setting, you really need to know and understand your data and the task you're being asked to perform in order to select the most appropriate search. But in terms of big O, theoretical efficiencies, binary search is always going to be more efficient than linear search. It's logarithmic versus linear, but it does require that sorted data. Now, one last note here about searching in the Java Standard Library. So we do have some searches given to us. You can take a look at the list interface, which of course is implemented by the ArrayList and linked list classes. And if you take a look at that, you can look at the index of method, which basically is a linear search. You're finding the index of an object in your list. Okay, so that's basically a linear search. There's also a last index of, which is also a linear search, except instead of stopping the first time you find a match, you keep going until you reach the end of the array because you're going to find the last match. So that would basically be taking out that not found clause that we looked at in our linear search code. Okay, so the index of and the last index of in lists, those are basically linear searches. We also are given a binary search method. So if we look at the arrays class, note that this is arrays with an S. This is a class that gives us a lot of static helper, static utility methods for arrays. This also has a collection of binary search methods. So if we take a look at that, you can see that there are a bunch of them. There's binary searches that take, doubles, chars, floats, ints, objects. Okay, so and there are also different versions where you can just pass in the array and the target. You can also pass in the array, the target, and a beginning and ending index. So if you didn't want to look over your whole entire array. Now these are static methods, so you would invoke them as arrays, again, arrays with an S, dot binary search, and then pass in your array and your target. Okay, so Java gives us these binary search algorithms, these methods built into the standard library, which is great. One really important thing to notice about this, or to know about this rather, is that it assumes, for example, if you're using the object version, let's say you have objects that you want to search, it assumes that those objects implement comparable. But it's not going to complain at compile time if it doesn't. It's going to complain at runtime, and it's going to throw a class cast exception, which is a really bad exception because those are almost entirely preventable from careful coding. So what you want to do is you always want to make sure if you're using this binary search on objects that those objects come from a class that implements comparable. If they don't, that means you can't do binary search, and you definitely shouldn't use this binary search method, right? If you use it, your code is going to compile, but when you try to run it, it's going to crash. So that is just something to be aware of. So there are your two main sorting methods, linear or sequential, and binary, and post any questions you have about those to the discussion board.